Hello everyone, this is another series of lectures on differentiation rules. We continue talking about different rules that we can use to find the derivative of different functions. So we have studied already the constant function rule, and then the power rule, constant multiple rule, and the sum rule and difference rule. These are all the five rules we have studied so far. Now we want to continue with product rule. Okay, so the product rule is like this. We consider a function y equals f of x times g of x. That's the product of two functions. And we want to find the derivative of this product, obviously. So we're going to say y prime equals limit of f at x plus h times g at x plus h, because we have a product function, minus f of x g of x all over h when h approaches 0. This is coming from the theoretical definition of the derivative of a function, okay? But our function here is f of x times g of x. It's that product. That's why we end up with f at x plus h times g at x plus h minus f of x g of x all over h. Now here, in order to find this limit and come up with a formula for the derivative of a product of two functions, we are going to use a trick. The trick is to add and subtract a particular term in the numerator. So I'm adding f of x times g at x plus h, and I'm subtracting the same amount, f of x times g at x plus h. So these two cancel out each other. I have not changed the problem. But the thing is that by using this trick and adding and subtracting a particular term in the numerator, I will generate common factors for the next step. So for the first two terms, g at x plus h is a common factor. I factor it out. And the last two terms, f of x is a greatest common factor. I factor it out. And I end up with this next line. Okay, limit of f at x plus h minus f of x, it's inside the brackets, times g at x plus h, which we factored it out, plus f of x, which we factored it out from the last two terms, times g at x plus h minus g of x. And the denominator is always h, of course. We take the limit when h approaches 0. Now, we just have to do a little bit of cleanup here. So this h belongs to all parties of the numerator. So we're going to break this fraction, big fraction, down into two fractions. So it's going to be f at x plus h minus f of x times g at x plus h over h, and then plus the second fraction, f of x, times that expression inside the square brackets divided by h. So we have limit of sum of two functions. We did have a giant big fraction, but we broke it down into two fractions, okay? And now we have limit of these two fractions in addition form. We know from the properties of limits that limit of a sum equals sum of limits. So I can write the limit of the first function here plus the limit of the second function. That's what I can do according to properties of limits. So now that I wrote it like this, I can say each one of these limits are in product form to tell you the truth. So we have one function times another function, that quotient. Here, one function f of x times another quotient, another function. So this is a product, and I'm finding the limit of a product. According to the properties of limits, limit of a product equals product of limits. Therefore, I can break this down as limit of the first function, g at x plus h, when h approaches 0, obviously, times the limit of the quotient function when h approaches 0. Because limit of a product equals product of the limits. For the same reason, this last part, limit of that product, would be limit of f of x times limit of that other quotient, okay? So now, if h approaches 0, I wonder what is limit of g at x plus h? Obviously, g at x plus h would approach g of x if h approaches 0. But this second quotient, limit of that quotient, is very, very famous in calculus. That is actually the definition of the derivative of f of x. So this whole limit here is going to be f prime of x. And you have used this many times, actually. And we use actually the same formula to write the very first line for our product function. Plus limit of f of x when h approaches 0. So f of x doesn't have any h in it, so we can treat that like a constant. And it doesn't matter if h approaches 0 or anything else. The limit of f of x would be f of x itself. And then times the limit of this quotient when h approaches 0, that is actually the derivative of g of x, so which is g prime of x. So let's see what we end up here. We were trying to find y prime, the derivative of the product function, and we ended up with g of x times f prime of x plus f of x times g prime of x. That is the final answer we ended up with. So the derivative of the product of two functions f and g would be derivative of f times g plus derivative of g times f, simply. Now, if we use letters u and v, just to make it a little bit informal and less intimidating, instead of f of x and g of x, if we can use letters u and v, where u and v are representing functions of x, okay, then this product, u times v, has a derivative which is equal to u prime v plus v prime u. Easy to remember, easy to memorize. Y prime equals u prime v plus v prime u. Derivative of first times second plus derivative of second times first. As simple as that. Same thing that we actually proved here. Now, there's an example here. We have a cubic function, 4x cubed minus 1, times a quadratic function, 5x squared plus x. So this is playing the role of f of x, and the other one is playing the role of g of x. Or, informally, one is playing the role of u, the other one plays the role of v. And we know that the derivative of uv, the derivative of product, is u prime v plus v prime u. So here, I'm going to find u prime, which is the derivative of 4x cubed minus 1, and that is 12x squared. So that is u prime. And then the formula says times v. So I'm going to multiply this by 5x squared plus x. So this was u prime, and this is v. And then it goes plus v prime times u. Now v prime is 10x plus 1, okay? And then I have to multiply it by u, which is 4x cubed minus 1. So this is u, and this is v prime, actually. So u prime v plus v prime u. Derivative of first was 12x squared times the second function, and plus derivative of second function, which was 10x plus 1, all right, times the first function, which is 4x cubed minus 1. Now, you can, of course, sit down here and simplify this by doing the expanding, doing the FOIL, and collecting like terms and simplifying, come up with some sort of polynomial function. But that is all algebra, that's all simplifying. It has nothing to do with differentiation or calculus. Calculus stops here, okay? So as soon as you find this line for y prime, then the rest of it is just algebraic manipulation and collecting like terms and expanding and simplifying and that kind of thing, okay? So this is the story of product rule, and that was the official proof of it. This was one example. That was the informal formula, easy to memorize, easy to remember, and that's all we need to know. Now, if you have more than two functions in the product form, if you have like u times v times w, let's say we have like 4x cubed minus 1 times 5x squared plus x, and then times a third function, some sort of third function there, or even like the fourth function and then fifth function, all in product form. If that is the case, then we are dealing with product rule extended. And product rule extended has a formula like this. If you have like 3 functions or 4 functions and 10 functions in the form of a product, you are going to take the derivative of the first, u prime, times the rest. Okay, so u prime times the rest, which means vw. And then plus the derivative of the second function, v prime, times the rest, which is u times v. And then plus the derivative of the third function, which is w prime, times the rest, which is u times v. And just like that, I put dot, 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 meaning that if you have like 4 functions, 5 functions, just like that, you're going to multiply the derivative of the first function by the rest, as many functions as they are, plus the derivative of the second times the rest, plus the derivative of the third times the rest of the functions that are there. Now, I don't know, 10 functions, 4 functions, whatever functions, okay? So this formula is known as the product rule extended, okay? I can just write it for only 3 functions if you want to keep it simple, but if instead of 3 functions, you have 4 functions in product form, or 5 functions or 10 functions in product form, you can just follow the same pattern. You just take the derivative of the first function, multiply it by the rest of the functions, and then plus the derivative of the second function times all the rest, and so on and so forth. So product rule and product rule extended. Okay. Now we want to talk about another rule, which is called quotient rule. Quotient rule, for the quotient rule, we're going to say h of x is like a function we define, is like f of x over g of x. Okay, and this is just a quotient, isn't it? And we want to find y prime, or I should say here, h prime. We want to find the derivative of function h, so we are looking for h prime of x. Okay, I used letter h here. Now, to find the derivative of a quotient, or h prime, I'm going to use a little trick here. So the proof of this is not going to be as complicated or as long as the other one, because of this nice delicate trick we are using here in the proof of quotient rule. So I'm going to cross multiply here. I'm going to say f of x equals h of x times g of x. All right? And then I'm going to say, hang on a second, this is a product on the right-hand side, isn't it? Therefore, I'm going to differentiate both sides of this equation. So left side will be f prime of x, and the right side, guess what? It's going to be the derivative of this product, which we already proved it. So it's going to be the derivative of the first function, g prime of x, times the second, plus derivative of second times the first, actually. So this is actually the product rule, right? Which I applied here. And all we need to do is to solve for h prime of x. That's all we need to do, because we are looking for h prime of x, which is the derivative of f over g, or the quotient, right? Quotient of f and g. So to find h prime of x, all I have to do is just do a little bit of algebraic manipulation and that kind of thing. So I'm going to go f prime. If you don't mind, I'm going to avoid writing brackets x just to keep it simple. So f prime minus g prime h equals h prime g. I'm going to write it in this shorthand form. And the goal is to solve for h prime. So obviously I'm going to divide both sides by g. So g prime h over g equals h prime. All right. Now I think we have a common denominator of g here. So that is going to be f prime minus g prime times h over g equals h prime. But instead of h, I can write f over g, because that's the quotient function, isn't it? So that's f over g. And now, doing the common denominator in the numerator, it's going to be g. And adding or subtracting the fractions in the numerator gives me g f prime minus f g prime in the numerator, divided by g, but then again divided by g, which means divided by g squared. So that will be h squared, basically. So I found the formula actually for this. So I can say h prime of x equals f prime of x times g of x minus f of x times g prime of x all over g of x squared. So this is the formula I derived for actually this so-called quotient rule. Okay, so we take the derivative of the top times the bottom minus the derivative of the bottom, g prime of x, times the top, which is f of x, divided by the denominator squared. So that is the quotient rule basically here. Now, in terms of informal notation, we can use u and v, where u and v represent functions of x. And we can say, okay, the derivative of u over v is u prime v minus v prime u. So u prime v minus v prime u divided by v squared. Okay, u prime v minus v prime u divided by v squared. Easy to memorize, easy to remember. That is the formula for the quotient rule. And I can give you a numerical example here. Y equals 2x minus 1 over 5x squared plus 1, for example. So what plays the role of u is the numerator, 2x minus 1, linear function. What plays the role of v is the quadratic function in the denominator, 5x squared plus 1. So we're going to say the derivative of this quotient is going to be the derivative of the top, which is 2, times the bottom, 5x squared plus 1, and then minus, not plus, and then the derivative of the bottom, which is 10x, times the numerator, which is 2x minus 1, all over the denominator squared. Okay, so this is the derivative of that quotient function, or that quotient or rational function. Now you can simplify, certainly, I'm not saying no. This is going to be 10x squared, that's going to be negative 20x squared, so that's negative 10x squared. Then we have negative times positive 10x, of course. And then here we have plus 2. I'm just expanding and collecting like terms all over the denominator squared. So this is the final derivative which we were looking for. So the derivative of the numerator is 2 times the denominator minus the derivative of the denominator, which is 10x, times the numerator this time, all over the denominator squared. So this is going to be 2 times 5, 10x squared, and that is negative 20x squared. Collect like terms, it's going to be negative 10x squared, and then we have negative times negative, positive 10x. So I write it down, and then 2 times 1 is 2. So that is the numerator in the simplified form after we collected like terms. And the denominator squared, we don't touch it, we don't need to expand it. We're going to leave it in that form. So the derivative of y equals 2x minus 1 over 5x squared plus 1 is equal to this big expression right there at the bottom. And we used quotient rule, whose formula is u over v. The derivative is u prime v minus v prime v divided by v squared. And you can easily memorize this formula, and by doing like few exercises, you will become very fluent in applying the quotient rule. So in this lecture, we proved the product rule. We also proved the quotient rule. These are the theoretical proofs. We gave you informal formulas, easy to remember, and I gave you one example of each. Is one example good enough? No, it's not enough. Is like 20 examples enough? Maybe not even 20 examples. You have to practice as much as possible, as much as you can, I should say, so that you master these differentiation rules, because it's going to be used a lot in future. And this is an investment you do for your future, because in university, no matter what program you go, 99% of programs that you apply, you have to take first year university calculus. And the textbook, actually, I have the textbook. It's right here. This is the textbook for the first year university calculus. You see how thick it is. It's, I don't know, a couple of thousand pages, to tell you the truth. It's like about 7 kilograms. Okay, so this is what is waiting for you in university. So the stronger your math foundation is from high school, the better, for you. And I hope you understood these two rules, and I'm going to continue with more differentiation rules in the next lectures. Thank you for your attention, and as always, keep practicing.